We all learn in school that atoms are the building blocks of everything. But for the longest time, everyone thought they were just these tiny, solid, unbreakable little balls. Well, today, we're going to crack one of those spheres wide open and take a look at the wild, dynamic world that's hiding inside. So, let's get started and journey to the very heart of matter.
So, here's our plan. First, we'll meet the tiny particles that make up, well, everything. Then we'll do a little time traveling to see how our picture of the atom has changed a lot. We'll get into the rules that atoms have to play by, figure out what gives an element its permanent ID, and even meet some of its weird relatives. And then, of course, we'll wrap it all up with a quick quiz to see what's stuck.
All right, let's kick things off. Our story starts back in the late 1800s. Scientists were wrestling with a huge problem. They knew atoms existed, but they had no idea what they looked like on the inside. The old ideas were about to get completely blown away.
And this was the million-dollar question. For ages, John Dalton's theory was king. The one that said atoms are the smallest possible thing, totally indestructible. But experiments with electricity and gases were turning up some weird results. It was starting to look like atoms weren't solid billiard balls at all, but that they had even smaller, charged parts hidden inside.
The atom didn't give up its secrets all at once. It was more like a long detective story that unfolded over almost 50 years. It started with Goldstein and these mysterious canal rays, which was our first big clue about a positive charge. Then J.J. Thomson came along and nailed down the identity of the tiny negative electron. But the puzzle still wasn't complete until 1932, when James Chadwick found that final crucial piece, the neutral neutron.
So let's officially meet our cast of characters. You've got the proton. Think of it as the positive heavyweight. Then there's the electron, its total opposite with a negative charge, but, and this is key, a mass so small it's almost nothing. And finally, you have the neutron, the neutral party, weighing about the same as a proton. Okay, so we've got our particles. The next obvious question was, how in the world are they all arranged? And that question led to some really creative ideas about what an atom actually looks like. The first couple of guesses involved everything from a dessert to a mini solar system.
So J.J. Thomson, the guy who found the electron, took the first shot. He came up with what we now call the plum pudding model. Just picture a ball of positively charged goo. That's the pudding. And then you've got these little negative electrons just stuck in there, like raisins. It's a simple idea, and it made sense at the time, but it didn't hold up for very long.
And this is why. A scientist named Ernest Rutherford came up with this brilliant experiment. He decided to fire a stream of tiny, positively charged things called alpha particles at a ridiculously thin sheet of gold foil. Now, if the plum pudding model was right, those particles should have just blasted straight through. What he found instead? Well, it changed everything.
So, let's break down what he saw. First, most of the particles did go straight through. Okay, so that means the atom must be mostly empty space. Check. Second, a few of them got knocked off course a little bit. That suggests they passed by something with a positive charge. But the third result was the real shocker. Once in a while, like 1 in 12,000 times, a particle would hit the foil and bounce straight back.
Rutherford himself put it perfectly. He said it was as unbelievable as shooting a cannonball at a piece of tissue paper and having it bounce back and hit you. It just wasn't supposed to happen. This meant the plum pudding idea was completely wrong. There had to be something tiny, super dense, and positive right in the middle of the atom.
And boom, this was his new model, a tiny positive nucleus in the center, with electrons orbiting it like planets around the sun. It's a beautiful picture, right? But it had a huge, fatal flaw. According to the physics of the day, an orbiting electron should be constantly losing energy. It should spiral inwards and crash into the nucleus in less than a second. Based on this model, atoms shouldn't exist at all.
So the atom was in crisis. Rutherford's model was brilliant, but it was also impossible. The stage was set for a new scientist to come in and save the day. And his name was Niels Bohr.
Bohr's big idea was actually pretty simple. He said, what if electrons have to follow rules? They can't just orbit anywhere they want. They're stuck in specific, stable orbits called energy shells. Think of it like a ladder. An electron can be on the first rung or the second rung, but it can't float in between. And as long as it stays on a rung, it doesn't lose energy and the atom doesn't collapse. Problem solved.
So how do we know how many electrons can be on each rung of the ladder? Well, there's a simple little formula for that. 2n squared. Here, n is just the shell number, starting from the inside.
So for that first shell, where n equals 1, the math is 2 times 1 squared, which is 2. The first shell can only hold 2 electrons. For the second shell, n is 2, so it can hold up to 8. The third can hold 18, and so on. This is the simple rule that organizes the entire periodic table.
So now we've got the basic structure down, let's look at how that structure actually gives each element its unique fingerprint, its unchangeable identity. I want you to think of every atom as having its own ID card, with 2 really important stats. The first, and most important, is the atomic number, which we call Z. This is just the number of protons. It is the one thing that defines an element. Carbon always has 6 protons. If you gave it a 7th, it's not carbon anymore, it's nitrogen. That number never ever changes. The second stat is the mass number, or A. That's just the total number of protons plus neutrons. It basically tells you how heavy the atom is.
Okay, now for a really important concept, valency. You can think of it as an atom's social life, how it interacts and combines with other atoms. And it's all driven by one thing. Atoms want to have a full outer shell of electrons. For most, that magic number is 8. So to get there, they'll gain, lose, or share electrons. Take sodium. Its electrons are arranged 2, 8, 1. It's got that one lonely electron in its outer shell. It could try to gain 7 more, or could just get rid of that 1. Losing 1 is way easier, so that's what it does. Its valency is 1. Now look at fluorine with an arrangement of 2, 7. It's so close. It just needs 1 more electron. Gaining 1 is much easier than losing 7, so its valency is also 1.
All right, let's clear up a topic that can be a little confusing for people. The idea of isotopes and isobars. The easiest way to think about them is as an atom's extended family.
Looking at them side by side really helps. Isotopes are atoms of the same element. They have the same number of protons, that's why they're the same element, but they have a different number of neutrons, so they weigh a little different. Isobars are different. They're atoms of different elements, so different numbers of protons, but they just so happen to have the same total mass number. They're like strangers who happen to weigh the same.
So why does any of this matter? Well, isotopes have some incredibly important real-world uses. Because while they act the same in chemical reactions, that difference in their nucleus can make them special. An isotope of uranium is what we use for fuel in nuclear reactors. An isotope of cobalt is a life-saving tool in cancer treatment. And an isotope of iodine is used to treat thyroid disorders. Pretty amazing stuff. Okay, we have covered a ton of ground, from plum pudding to planetary orbits and atomic ID cards. So I think it's time to put what we've learned to the test. Just a couple of quick questions.
First one. Rutherford's famous gold foil experiment led to the discovery of what? Was it the electron, the proton, the nucleus, or atomic mass? Think back to that cannonball bouncing off tissue paper. What did that tell him had to be there? The answer is C, the nucleus in the atom.
And for our last question, if an element has a valency of 1, is it always a metal, always a nonmetal, or could it be either? Remember our examples. Sodium is a metal that likes to lose 1 electron. Fluorine is a nonmetal that likes to gain 1. Both end up with a valency of 1, so the answer is C. They can be either metals or nonmetals. And I just want to leave you with this one final thought. We've gone from thinking the atom was a solid ball to this complex system of shells and particles, and each new model built on the one before it. It really is a perfect picture of how science works, and it just makes you wonder, what other secrets about how the universe works are we just about to uncover? Thanks for joining me for this explainer.